January 15th, 1990. Mid-afternoon on a Monday. Inside AT&T's Network Operations Center in Bedminster, New Jersey, there is a wall-sized map of the United States. Every long-distance switching center in the country is a light on that map. Normally, the lights sit quiet. At about 2:20 in the afternoon Eastern Time, they start turning red. Not one, not a cluster. Red spreading across the board like a stain, and the calls stop going through. Operators in that room are watching a national telephone network fail in real time, and nothing has been cut, bombed, or flooded. Nothing physical has broken at all. By the end of this file, you'll be able to explain, in plain words, how a single instruction placed in the wrong spot inside one program brought down a network built specifically so that no single failure could bring it down. You'll know why the redundancy made it worse instead of better. And you'll know why the engineers who designed that network were not careless. They were, in a very specific and documented way, unlucky in exactly the manner Murphy's Law was written to warn about. Start with what people believed at the time, because in January of 1990 almost nobody guessed software. The assumption, then and now, is that a national outage needs a big cause, a cable severed by a backhoe, a fire in a central office, sabotage. And that assumption is reasonable, because it's usually right. Phone networks did fail that way. A single trench, a single flooded vault, a single fire, and a region goes dark. So when calls stopped in 1990, the reasonable first thought was that somebody, somewhere, had physically broken something large. Reporters asked about hackers. Some callers assumed a storm. Everyone was looking for damage. And there wasn't any damage to find, which is where the case gets interesting. Here's the first piece of evidence. The switches involved were AT&T's 4ESS machines, the big electronic switches that handled long-distance traffic between cities. In 1990, there were well over 100 of them across the country. They didn't just carry calls. They talked to each other constantly, using signaling messages sent on a separate network, so a switch could tell its neighbors what it was doing and how busy it was. That signaling network is the important detail. The calls and the conversation about the calls traveled on different paths, which meant a switch could sound broken without being broken. Second piece of evidence. In December of 1989, roughly a month before the outage, AT&T had loaded new software into those 4ESS switches. The upgrade was meant to make recovery faster. When a switch had a problem and had to reset itself, its neighbors were supposed to notice quickly and route around it, rather than waiting and wasting time. That's good engineering. That's the whole point of a resilient network. The change touched the code that handled incoming signaling messages, and it went out to every switch, because every switch needed to speak the same language. Hold on to that word. Every. Third piece, where the outage started. The contemporaneous trade reporting in telephony describes an internal problem in trunk interface equipment at a switch in New York City. Not a self-test. Not a maintenance error by a person in the room. Something inside the hardware misbehaved, and the switch did exactly what it was designed to do. It took itself briefly out of service, corrected itself, and came back. That is the safety behavior working. A machine noticing it was unwell, stepping aside, fixing itself, and returning. In a well-designed network that's a non-event. It lasted seconds. Fourth piece. When that New York switch came back, it did what the new December software told it to do. It sent a message to its neighboring switches announcing it was available again, and it started accepting calls once more. Perfectly normal. The neighbors received that message and began updating their internal records to show New York was back. And while a neighbor was in the middle of doing that bookkeeping, a second message arrived from New York. 2 messages, arriving very close together. Milliseconds apart, that timing is the whole case, because of what the code did next. 5th piece. What happened to the neighbors? Each switch that got caught in that timing decided its own internal data had gone bad. And again, it did the responsible thing. It took itself out of service to reset and clear the corruption. That's the fail-safe. A machine that suspects its own memory is wrong should not be handling live traffic. So it stepped aside, reset, and came back. And when it came back, it announced itself to its neighbors and started accepting calls, and you can already see the shape of the problem forming on this board. 6th piece. The spread. Every recovering switch broadcast its return, and that broadcast landed on neighbors who were themselves recovering, or busy, or about to be. So they reset, which produced more announcements, which reset more switches. The failure traveled along the signaling links, which were fast and reached across the country in minutes rather than hours. The network's own health reporting system had become the delivery mechanism. Reports at the time described the outage running nearly 9 hours before it was brought under control. The record I can rely on does not fix a precise minute when everything came back. So, the mechanism. Inside that December software there was a section of code handling the incoming signaling messages, and inside it, a decision structure. Do one thing in this case, another thing in that case. Programmers separate those cases with a small instruction that means, stop here, don't fall through into the next case. In the C language, it's called a break statement. In this program, one of those break statements sat in the wrong place, slightly too deep inside a nested block when it needed to be outside it. One instruction, one position. The consequence of that misplacement was narrow, almost invisible. It only mattered if a second message arrived while a very specific piece of bookkeeping was still in progress. Miss that window by a few milliseconds and nothing happens. Hit it, and the switch overwrote data it should have left alone, then noticed the damage and reset itself in self-defense. The code was not broken in general. It was broken only in a timing window most calls would never touch, which is exactly why testing didn't catch it. You don't find a millisecond-wide fault by trying the switch a few hundred times. Now the part that should bother any engineer. The redundancy is what spread it. Over 100 switches, and the network's strength was that no single one mattered. Lose one, route around it. But they were all running the same software load, so they all carried the same misplaced break statement. Identical machines share identical flaws. The diversity that would have saved them, different code on different switches, was the same diversity that would have made them incompatible. They couldn't have it both ways. The backup was a copy, and a copy of a mistake is still a mistake. And notice what all the safety features did. The New York switch protected itself by going out of service. The neighbors protected themselves by resetting when they suspected bad data. The December upgrade existed to make recovery faster. Every single one of those behaviors was correct in isolation. Chain them together with one instruction out of place, and the protective reflexes become the outbreak. Nobody wrote a dangerous system. They wrote a careful one, and one line let the care run in a circle, which is why this reads, to almost everyone who hears it, as bad luck. It feels personal because of what you don't see. That switch in New York had a small hardware complaint and recovered normally, and it had almost certainly done something similar before without incident. Thousands of switch recoveries had happened across that network since December without triggering anything. Those are the invisible cases. You only ever notice the one where the timing landed inside the window. If this kind of case is your sort of thing, subscribing keeps the next file coming, because the pattern here shows up in a lot of places that have nothing to do with telephones. That asymmetry is the entire illusion. The near misses leave no record. Nobody logs the afternoon where a switch recovered and its neighbors updated their books with 2 milliseconds to spare. So the successes are invisible and the failure is on the front page, and from the outside it looks like the network was fine and then cursed. It wasn't. The fault was sitting in every switch in the country for about a month, waiting for a coincidence in timing. It was already there on January 14th. Nothing changed on the 15th except the arrival of the right accident. What the record does not settle. Accounts differ on the exact scale. Contemporaneous reporting and later retellings give different figures for how many calls were blocked and how much revenue AT&T lost, and I'd rather give you a range than a false precision, so treat any single dramatic number you've seen with suspicion. The precise moment full service returned isn't something I can pin down from what I trust, and the fine detail of the code, how the nested block was written, comes to us second-hand through engineering write-ups and post-mortems rather than a published listing. The break statement is well attested. The exact source lines are not. One more thing worth pinning. Murphy's Law didn't start as a complaint about fate. It came out of aerospace testing, from engineers whose job was finding the way a part could be installed wrong, so it could be redesigned to make that impossible. It's a design instruction. If a fault can happen, assume it will, and build for it. The 1990 network was built by people who understood that. They planned for a switch failing. They planned for a cable cut. What they had not planned for was every switch failing the same way at the same time, because every switch was the same. So the lesson from this file isn't that machines betray us. It's narrower and more useful. When you copy a system to make it safe, you copy its faults too, and a network of identical survivors will all die of the same thing. That principle outlived the 40SS by decades. It's in the software running on your phone right now. Next file, we go from a fault that spread too fast to one that hid in plain sight for years, on a machine that was inspected constantly by people who knew exactly what they were looking at.